Okay, so what I'm talking about today, I'm trying to have a very modest aim. Essentially, I just want to explain this picture down here. Okay, so this is the main aim of the talk. The context where this appears as an illustration of Yixian's formula, and the context is intrinsic mirror tree setup that did together with Mark, where we start with a log Calabi-Yau, a pair x comma d, and we construct. Now we want to construct a wall structure. So in the intrinsic mirror symmetry, we just the paper that's out since last year, we just constructed the homogeneous coordinate ring of the mirror directly using punctured invariance. Now we want to connect it to our previous constructions using wall structures and constructing theta functions via wall structures. And I'll sketch how this goes a little bit, but I won't go into the details because I really want to focus on that computation down here. But essentially, the story is we start with a log Calabi-Yau, and then we get a dual intersection complex for this pair. That's essentially a simplistic complex P and an underlying topological manifold B. And on this topological manifold, we define a wall structure entirely using tropicalizations of punctured curves. Once we have wall structure, we can define a notion, what we call broken lines. They're depicted here. This would be something like a broken line. Okay, so it's something, it's a piecewise linear object that meanders through your topological manifold and can bend or cannot bend at the walls. Okay, so here's one wall, it's a codimension one object, and then you go through it transversely and you bend. And that leads to the main main topic of the talk. The way they bend has been defined by us previously in a purely algebraic way. So we have walls, and it's a simple rule of expanding, of kind of multiplying your monomials by certain polynomial functions carried by the walls. And then you just pick up certain coefficients that dictates you how to continue through the wall. Okay, so that was a purely algebraic condition. And now with the new technology of punctured invariance, we understand the kind of picture we had in the back of our mind throughout the whole time, namely that what we are doing secretly is kind of, these things should be tropicalizations of certain broken lines, as well as all the stuff living on the walls, certain tropicalizations of curves and of logarithmic curves. And the way this interaction works is by a gluing formula telling you how certain punctured curves, punctured maps, glue to things of to punctured maps of a different kind. Okay, so that's roughly what I want to explain. And obviously there will be a little bit of setup and notation I have to tell you before being able to write down a formula. So let me briefly sketch this intrinsic mirror symmetry setup. And I only want to do this in the what we call the absolute case, where you have a pair x comma d. There's another case which is relative, where we would have a degeneration. It's called maybe x. There's an x0 in x, and that degenerates over, let's say, the spectrum of a discrete valuation ring, and you have a closed fiber. That would be the relative case. And I'm not going to talk about this case, okay? So let me just remove this here. So we take the absolute case, it's just a pair. D is a simple normal crossings divisor. And I assume that oh, did I say that this is work with Mark Rose? It's written here, but I didn't say it. And obviously it all builds on this long collaboration with Dan, Abramovich, and Chen on punctured Gromov-Witten invariants that we finally finished just 2 days ago. Okay, so we start with these, assuming that the logarithmic tangent bundle, oops, that shouldn't happen. The logarithmic tangent bundle that log geometer would just write as theta x, more traditional algebraic geometer would write theta x log d. So with logarithmic poles along d, is numerically equivalent over the rational numbers to a divisor, to an effective divisor supported on d. Okay, so d is obviously sum of di's. These are the irreducible components. And then there's some divisors that are kind of good from the point of view of log geometry. These are the ones where the AI is 0. So if you think of actually a holomorphic form with poles along D, these are the ones that have logarithmic poles. You know, where your form, where a section of theta x log D has first order poles. Okay, so for example, down here, I just gave this for the easiest example I could imagine of. Let's blow up, which is kind of showing something non-trivial. Let's take the blow up of P2 in one point, producing an exceptional divisor. Now D is the union of all these 4 components, but the good divisors are just this kind of these 3 lines, and the exceptional divisor is not good, okay? And then you produce of this the dual intersection complex, ignoring only taking the good divisors, okay? So this has a central point which corresponds to the empty intersection, and then the vertices, or the rays, the rays are given by the divisors, the good divisors, and then the deeper strata have 2-dimensional things and so on. That's typically considered Solomon skeleton, certainly in the relative case, but probably also in general. So we get a simplicial complex, and we tell B to be the underlying topological space, topological manifold. So that's the arena where everything is happening. We will need a few more kind of, let me first explain this. So if you go back in this picture, there's a sense in which we need to tell how to bend here, yeah? So there is something like an affine structure at these points that have to do with telling you, you need a local chart in Rn that tells you what a straight line is. Okay, so how do we define this affine structure? And that affine structure can be defined entirely in terms of intersection numbers. So how do we do this? The affine structure actually only lives in codimension 0. Well, this is easy. We have a normal crossing thing, so obviously there's these things are just copies of R larger or equal 0 squared in this case, maybe n in general. These are the deepest points. They correspond to the deepest points. And then we want to say what it means to go across a codimension 1 stratum. So the codimension 1 strata on B or in P correspond to the curves in D, the dimension 1 strata in D. So if you have a dimension 1 stratum, that's one of those things. You can write it as the intersection of n divisors. And then I just have to define a fan that tells you how to get the affine structure at this point. And where is it? E1 to En, E2 to En is here. You have to tell how to go from one side to the other. And you do this by writing down a fan where you just take the standard coordinate vectors E1 to En and one more vector that is dictated oops, changed again, by these intersection numbers of the dimension 1 stratum with all the other divisors, the adjacent divisors. In the relative case, Nice's Xu and Chengyang Xu and you, Tony, showed that this curve is actually a P1, and the other strata hit this P1 only in 2 points. So it really looks toric. It's a toric P1, and that will be very crucial because remember from Yixian's talk, we can do gluing along toric strata very easily and very, very efficiently with this beautiful formula. In the absolute case, there's a little bit of insecurity currently. If that still holds, maybe we have to put in a few more assumptions that I want to skip. Okay, let's assume that we are in a situation where this actually holds. And then in such cases, because we are normal crossings, that restriction of the log structure to this curve, to this P1, is actually idealized log smooth, like what we talked about in the last talk. So meaning it looks like the toric strata in some usually high dimensional toric variety, which we don't care what it is, but it is just something. The only thing we care about is that the log structure has a linearization along this curve, and that will always be the case if that's a toric variety, and you can take any log structure where this characteristic sheaf, the M bar, what we call the ghost sheaf, is constant on the strata. Okay, so that's the situation. So where are we? We now have a manifold B with a simplicial structure given by P, and along the codimension, in codimension 0, or let's put it this way, away from codimension 2, we have an affine structure, an integral affine structure. Okay, so in dimension 2, it would be away from the origin. That's the only place where we would not have an integral affine structure. Okay, so this is the setup. And then we are ready to define walls very easily. If you buy what Dan told about punctured invariance, it goes as follows. So Dan already reminded you that the integral points of this B, which, not sure, was it in his talk? What did he write it? Did he write it as B, or did he write it as maybe as sigma of X of Z?
Sigma of X.
Okay. So now it's called B of Z. These are the integral points on B in any chart. And that's a non-negative contact orders with D. So for example, let's look at this example that I had on the first page. This is B2 blown up in 1 point. You could take the integral points 3, 2. That kind of cell corresponds to this point here in the geometric picture, and saying 3, 2 means you have contact order 3 on one side, contact order 2 at the other side. So for example, a cuspidal curve would have this requested contact order. So this is the first ingredient. We need these contact orders. And then in addition, we need a homology class, as usual, a curve class. And well, that's the contact order U. And now we use a one-pointed Gromov-Witten invariant. Okay, so only 1 point will go in. Will hit D, at least virtually, of class A, contact order U, and then we fix a tropical type, which is actually maximal dimensional, which will be sorry, minimal dimensional, n minus 2. Sorry, it's maximal dimensional, n minus 2 dimensional. Is that right? Forget about maximal, minimal. It's n minus 2 dimensional, okay? Let's look at the example I had on the first page with this blow up in 1 point of P2. You find one line here. Yeah, that's a strict transform of the line going through this point and the blown up point. And that line contributes to this count, to this one punctured Gromov-Witten invariance. Actually, here it is a positive point. So this gives this kind of, well, it gives a number. And then also that was in Yixian's talk, you have an evaluation map, which is the endpoint of the tropicalization. So the tropicalization of the curve would be this whole thing. Yeah, so if you take that curve here, this line, view it as a punctured stable map. It's actually an ordinary Gromov-Witten map. It has one point of contact here. And take the tropicalization, it will be this kind of thing. So it has one vertex and one outgoing leg. Now in Yixian's talk, she had this evaluation map, and the evaluation map took a point on this puncturing leg, which here is a marked leg, and you vary it, and that will sweep out that leg. And you define your wall, P, that's a frag P, by the image of the endpoint of this tropicalization. Okay. So let's repeat this because it's a little dense here. The tropical type, I'm mixing up tropical types and the corresponding moduli space of tropical curves. In this case, it's a bit silly because tau is just this one point, right? So tau, this is a rigid curve, so tau will actually be, n, the natural numbers. But then you have the universal tropical curve over it, and you can evaluate this at this point and let it vary, and that will sweep out that whole wall, that whole leg. In general, you get a codimension one thing. Okay, so I'm trying to draw a three-dimensional picture here. In this case, you have something that I cannot draw very well. You have some cell sigma of any dimension in P. And you get this evaluation map of this kind of enhanced cone, the one which tells you also the puncturing points on the legs. And this is evaluation map at this one point, which goes from T tilde to sigma. The one I just told you about here, right? That would fix this point, would give that point. And that sweeps out this wall. Now, how do we, so that's just tropical geometry. It doesn't have any invariance. So let me record also these one pointed or one punctured Gromov-Witten invariant. We denoted NAU tau. And we write down this function, the formal power series. Maybe you want to cut at some power of t. That's our deformation parameter that we want to work over. So this whole thing lives in some power series ring, maybe something like CT. And then actually this is wrong, the other way around. So you have some coefficient ring, which is actually it's lambda p. Okay, so this is the tangent space of P intersected with the integral points on sigma. So this is some codimension, Z to K. And then form a power series with T. Okay, that's what it is. And that lives on this wall. Okay, we call this the wall functions. So it's some information, numeric information carried by the wall. It lives over here. Yeah, the Z is a tangent vector on the wall, and that's just there. Now, the second thing I wanted to do, let's go back again to this very first picture. So I've told you what this wall is in terms of they carry the information of one punctured Gromov-Witten invariance. And the puncture tells you how to interact with D. And And then I'm trying to define next these objects, which are called broken lines. They can also be defined with punctured invariants, but they depend on two contact orders. The one comes from infinity, so to speak. That's my P. So this tells you how to interact with D. And then you go in, and the other contact order lives on some cell sigma, so that the whole setup depends on the choice of some sigma that typically you take as a maximal. Let's use this maximal at this point. And this u will be a tangent vector, an integral tangent vector in this outgoing cell. So you should think of a stop point, an end point of this broken line, where this contact order lives. Yeah, let me draw another picture. So if B is like this, and you have all your walls, so what we have done is we have fixed a P coming from infinity, and then some point here in a tangent vector U. Okay, and the broken line will then connect the two in the way I sketched. So how do you do this? They will be obtained as tropicalizations of two punctured stable maps with two contact orders, one P, the other U. Okay, so to set this up, I also have to fix a curve class and a tropical type. Right, once you have a broken line, it comes with a tropical type. So I fix this type, and then I get this invariant, like Dan sketched. And then there's a procedure. At this point, I can just define functions that depend locally on this endpoint. Okay, in these Laurent polynomial rings that live here. So this is something like C and then lambda sigma. That's actually just a C of T1. I shouldn't say T. Z1 plus minus 1 to Zn plus minus 1. And then maybe form power series in T. Okay, so you get this formal expression that to make sense of it, you may want to cut off T a little bit, but it's a priori a formal function that is now defined at any point Q once you fix U and P. Okay, and in this paper with will come out, this is a little book in the memoir AMS with Mark and Paul Hacking. We showed that if there's a certain condition on this wall structure, consistency, then actually you can use this definition to define the homogeneous coordinate ring of the mirror. Okay, I'm not going to tell anything more. I want to view this as a black box. Okay, so I'm just saying, once you have a consistent wall structure, you get a mirror. Maybe I should pause for questions. The only thing you should take from this at this point is there's some way to get wall structures. They have to do with one punctured Gromov-Witten invariance. And then there's this weird notion of broken lines. They depend on two contact orders and two punctured Gromov-Witten invariants. And you take tropicalizations of the corresponding punctured maps, and they give you what look like these, what we defined as broken lines before. Yeah, so this thing, together with some other dirt, yeah, that I haven't mentioned, will be the tropicalization. So this is part of the tropicalization of a punctured curve. Okay, so essentially I'm now ready to come to the main topic of the talk. I want to show that these log theoretic broken lines agree with broken lines from scattering. Okay, so the rule, the kind of the algebraic rule to compute the theta functions out of a wall structure, they just tell you how it's a certain rule that is local to a wall. So whenever let's go back to the first page, because that's exactly the picture I want to talk about, right? So whenever a broken line like this one, let's say this is the endpoint Q, okay? Sorry, this is not the endpoint Q. That's not what let's say the endpoint Q would be here, okay? And now you just kind of go on until you hit the next wall. This is this wall P. And then the rule in this paper with Paul Hecking and Mark tells you how to bend by picking up some algebraic stuff that lives on the wall, okay? So I call this the GHS theta functions that you obtain when you obtain P and Q. Well, I haven't told you exactly. Let me see. Right. Oh, I skipped that. I should have mentioned this here. So of course, for the theta functions, you don't fix a type. You sum over all possible types. Okay. So the theta functions will only depend on P, the contact order, that parameterizes a basis of your O of 1 bundle, and then this outgoing point. And then the point is, of course, you vary Q, and you want to see how this changes, this formula, and that will tell you how to glue these together to honest functions that eventually define this homogeneous coordinate ring. Okay, so this is what you get here. This is just from, you get this side from walls, from consistent wall structure. Well, actually, at this point, yeah, maybe I don't even need consistent at this point. Just by an algebraic procedure from any wall structure by purely algebraic process. Has nothing to do with Gromov-Witten invariance, okay? And on the left-hand side, I get these logarithmic theta functions at any point. So, and the whole point of this talk is to show you how Yixian's formula can be used to give a very simple and transparent proof of this fact. Just by showing you that the bending rule, the algebraic bending rule that you get to get the broken lines, to tell you how broken lines pass through walls, are encoded, just reflect a gluing procedure of punctured Gromov-Witten invariance. Okay, so then this paper that was already mentioned with Mark, that is hopefully still coming out this year, apart from this thing, will also show that the log theoretic wall structure is consistent. So we can apply the procedure in this book to get theta functions. And the structure coefficients for these theta functions are exactly what we did without worrying about wall structures in the intrinsic mirror symmetry paper from last year. I'm not going to talk about these 2 points, okay? So I'll just talk about that aspect here.
I have a stupid question. So you talked about something like infinity, that needs to be some infinity. Do you work in a non-compact situation somehow?
Right, so it's, I'm just talking about the absolute case, X comma D, and then B is indeed a cone complex. It's,
I see. And
I said
if you
something wrong. It's not a simplicial complex, it's a simplicial cone complex. Okay.
Mm-hmm. And in the case of a degeneration picture, you would also have some infinities. That...
Right, you essentially have to work in the cone over this whole picture, yes.
Yeah, okay, thanks.
Yeah. That's right. You know that, right? I'm sure you know that. Okay, so let's see what's going on. And so this is one of the things I told you about that you cannot do so well in other setups. So I'm saying...
Sorry, Ben, maybe I also have a question.
Yeah, go ahead. Go ahead.
There is some log smoothness assumption somewhere here.
Yeah.
Okay.
Yeah, so Right. So if we work with maybe something that is more to the heart of a birational geometer, yeah. So maybe a DLT log Calabi-Yau, you would first resolve, and then show that what you get is independent of everything. But I already started with normal crossings, so that's log smooth. Yeah, the x comma d is x is smooth, d is normal crossing.
Okay, cool.
But can you resolve non-crappantly?
We don't care.
That's a separate question somehow.
Yeah,
makes sense.
Yeah, we don't want Crappant resolutions here. I mean, this is all this business with the AIs that we throw away. Yeah, they don't. We have to be careful to show that it actually doesn't interfere with the picture, but it's okay. So so what I wanted to show is that thing. Oh, this was the wrong. I have to draw correctly. Okay, so what's the situation? I have this incoming broken line. So it's just a reflection of a situation where I have some vertex here, some last vertex in your two punctured Gromov-Witten invariant, or tropicalization of a two punctured Gromov-Witten invariant, that contributes to a broken line. So where I had like a point Q somewhere here, let's say, okay? And you just continue in the outgoing direction. That was this outgoing contact order U. Okay, but let me remove this again because it will interfere with the other picture. And actually, I did not want to. Okay, let's start all over. I wanted. Oops. Still requires some practice. So I just wanted to take that stuff. Okay, let's put it here, not to kind of literate the picture. Okay, so then you have this stuff that lives on the wall. Okay, so this is stuff that comes from one punctured Gromov-Witten invariants. They only have these outgoing contact orders, so something here, and it comes from somewhere. Yeah, you don't know, and we don't care. Okay, but it lives on this wall, and it's a little hard to draw, but this leg, I mean, where it comes from, that might not live in the wall. It can come from anywhere. So, so then let's take that thing here. So there are all these things living on the wall. It's not just one.
Bernd, let me just ask you that last thing you said. That the thing which is living, the thing that has to do with A1 curves, thing that only touches once. You say that little T2, it doesn't live in the wall. It lives in the union of walls, right? Or
yes, it lives in the union of walls.
Oh, okay.
Exactly. So I could have drawn, but I'm so bad in drawing. I mean, it's like, it could be like this, right? This is where this would live. Does it make sense? Sean?
Got it.
Yep, okay, very good. Okay, so let's, oops, wrong thing. Let's get this away. So, and then what will happen is that at this point where they come together, they can interact. And interaction means you will have to introduce another component, which will give a vertex. And this component, it will look like this tropically, will be a punctured curve of type with just one component virtually, okay? So that could still split, but then it has a bunch of legs. And the number of legs you need is, there's one leg for each of the things living on the wall that you want to interact with, and one leg that comes from the incoming stuff. And then to continue through the wall, you will also need an outgoing leg. Okay, so this is the picture you glue in. This is what you want. So these are the ingredients in kind of Yixian's formula. Yeah, so Yixian had some tropical type tau. that is the union of all the things you see. And then you split at a bunch of edges. And the edges you split are these here. Okay, so in the picture, there are 4 edges that you want to split. And once you do this, you get your collection tau in, tau 1 to tau 3, and tau 0. Okay, so these are the things that appeared on the right-hand side of Yixian's formula. Okay, so we start with, so how am I doing this time? I have another, 15 minutes? Is that right?
A bit more than 20 minutes.
Oh, 20 minutes. Okay, very good. Okay, so let's take a minimal cell containing this wall. There are 2 cases, and they have to be treated slightly differently, but not fundamentally differently. So either this wall lives in a maximal cell, and in this case, the gluing stratum, just like the case of the degenerating cubic that Yixian talked about, is just a point. So a point, of course, is toric, no problem. The other case is when this minimal cell of P, that was the cone complex, yeah? Let me write this. So that was in P. So P is not part of the cone complex, don't get confused, right? P was just some polyhedral subset that lives in some cell, yeah? So it could either live in a maximal cell, or the smallest cell containing it is a maximal cell. So it hits the interior of a maximal cell, or it lies in codimension 1, okay? Because the dimension of P is n-1, that's the only 2 cases. And in this case, we want to use that it's a P1. So now I have to go back. Let me see if I can. Where was that? Oops, I have to go up over here, right? It was this statement I had here. Okay, so that all the one-dimensional strata are where are we? We are here. All the one-dimensional strata are P1s with their toric log. I mean, not with their toric log structure, with a toric log structure. Okay. Okay, so let me remind you of what Yixian just talked about. So you split this tropical type tau. There was a thing after going through the wall, together with all the tentacles going through unions of walls. You split along these edges E1 to ER. In the picture, it was these 4 legs that split. And then we get a splitting morphism that was finite and representable between the moduli spaces. Okay, that's just this map. Obvious. Kind of, this is not hard. This is really not hard. So essentially, what you do is just, okay, take a curve. It's marked by all these kind of subgraphs of the dual intersection graph. You group your components of the domain together and restrict your map to this domain. And then nodes become punctures, but that's all taken care of by this type thing. So this is the map. You just split by restricting your punctured map to various subcurves of your domain. Okay, so that's a splitting morphism. And then I assume that all the gluing strata are toric, and I take a generic displacement vector to apply some version of the Fulton-Sturmfeld formula for these Artin stacks. And then the formula looks like this. Okay, so you can push forward your virtual fundamental class, and you get a sum of products of virtual fundamental classes, but not of tau I, but of rho I. And these are certain substrata in this M of X tau I that I'll tell you about in a minute. And then there's a coefficient that has to do with the lattice index. I'm not going to explain this. You can imagine something you write down tropically. It involves lattices. You compute the index, and you divide it by the automorphism group. So the key thing to understand is really, what do we sum over? I hear myself. Somebody has to mute himself or herself. Okay, thanks. So what is this? So delta of W, that depends on the displacement vector. And it is a perturbation of each of the tau i's. So what's a perturbation? A perturbation in tropical geometry means it's actually a specialization on the algebraic geometric side. Okay, so you have some stratum that itself has this moduli space, that itself has substrata. Where are we? This guy, m of x tau I, that are given by these types, m of x rho I, that look like more complicated tropical curves. So the rho i's are perturbations, meaning it's probably easier to think the other way. So each rho I has a degeneration to tau I. So there's a family of tropical curves degenerating to tau I that are defining this type rho I. Okay, and we want the collection of the rho i's to patch together to a perturbation of tau when we take into account this displacement vector. So I'll give a very simple picture in a minute. Bear with me for so long. So we get a certain collection of these types, and then we want to kind of this to be minimal. Yeah, of course there are substrata of this guy, and they also appear in this moduli space. Well, we care about the minimal dimensional one, which means the maximal dimensional strata. Okay, so the dimensional form is as expected. Yeah, so the NE, this is where your displacement vector lives. And it's a transverse intersection. So meaning, if you impose on this collection of rho I, NE times, or dimension of NE conditions, you end up with tau tilde. Okay, so that's the dimension formula. And well, what is this tilde? Well, that's again this, and what are all these tilde? That was a tilde log structure that appeared in Yixian's talk. I'm sure nobody remembers. That was tropically the things where you, in addition to your tropical curve, fixed points on the outgoing legs. I had this in, where did I show this? Here, right? It is this additional information, okay? So let's go back. Okay, so let's do some very simple example. So Yixian did a more complicated example, but to make sure that everybody understands this basic picture, let's do the easiest example that we discussed. I mean, I discussed with Yixian at the beginning of the project, and was like the easiest case. Nothing fancy is going on here. So what is this? You take P1 cross P1 and degenerate it into a union of two copies of P2, and that's depicted here. So this is actually not an absolute case, but never mind. So this is actually a case over a standard log font. Okay, let me take C maybe. Okay, so this whole thing lives over the standard log point. And then I want to compute or do Gromov-Witten theory for curves of type 1,1, of degree 1,1. So they would degenerate into a union of two lines, one line on each of the P2s that you see here. So the toric diagram you get is depicted over here. And that's actually the cone complex, sigma of x, or rather, it's a height 1, okay, thing of the cone complex, okay, height 1, intersected with height equal 1, that comes from the map, the tropicalization of the projection to this standard log point that you have here. Where is it? So here's a projection pi. And then this is a tropicalization of sigma of pi, and that goes to the tropicalization of the standard log point, which is a positive real axis. So think of a cone over this thing, okay? And then you see here the fan of P2, here the fan of the other P2, and that would be prescribes this degeneration. So this guy here, oops, this guy here reflects is dual to this gluing stratum. So the gluing stratum is a P1, okay? And we want to go two lines. Now, quite obviously, the ones that appear in the on the center fiber, they don't look like this, like the one I drew here, but they would have to match. So I'm drawing an amoeba-like picture of a line. So they have to match here. Yeah. So these are the geometric pictures of degenerations of 1-1 curves to the central fiber. But if I glue, I would look at, if you look at this diagram, where is it? The splitting map. Yeah. So what is this? The splitting map tells you that you take two moduli spaces. So S would be 2 here, each of a line on this P2. And yeah, you split the curve. Yeah. So you split the glued curve and put them up. Put it apart, pull it apart over here. So what you get is these moduli spaces on the right-hand side. Sorry, we are here. That's just the moduli spaces of pairs of lines in the central fiber. Okay. Now let's take for tau. What is tau? Tau is the type of the rigid tropical curve that is hard to draw because it's just the one skeleton of sigma of x. Okay, it just agrees with this picture, but that's a coincidence in this particular situation. Okay, it's just saying, indeed, there's an element of the moduli space where this point, this vertex, this irreducible component maps to the interior of this component. So this maps to that vertex. Similarly over here. And then you have these tentacles telling you that we have first order intersections with the toric divisors. Okay, so the interesting stuff is the splitting edge. That is this thing, which in this case agrees with this edge in sigma x. So the formula depended on the choice of a generic displacement vector, and that's where the formula becomes, I think, especially useful, because you can choose your displacement vector at however you like. Okay, you can adapt your displacement vector to your special geometry. So here it doesn't matter much, but in the application it will. So let's say we take as displacement vector here something like 1, 0. And then delta of W has 2 elements. So we have to split that curve apart. But remember that minimality condition that tells you that if I split, I should only increase dimension by 1. So what are the types that you get where you increase dimension only by 1? Well, one still has to stay where it was, and the other has to be displaced by the displacement vector. And there are only 2 ways to do this in this particular situation. You can either move that one to the left or that one to the right. Okay, and you check the dimension formula indeed, the dimension rho I tilde. Let's check it for 1. Let's just make sure we did this correctly. That kind of moduli space is 2-dimensional. It looks 1-dimensional, but remember it's all cones. So this is a 2. Then we have the outgoing point that adds a 1. And then the rho 2 is similarly just 1 plus 1-dimensional. Okay, so this is from the rigid thing plus this outgoing point. And that's the same as the dimension NE, which here is 3. Yeah, cone over this, we're in a 3-dimensional space, cone over 2-dimensional space, so to speak. And the dimension tau tilde is 1 plus 1. So indeed that works. Okay, questions? Let's make sure that everybody understands this basic. I think this is, if you understand that slide, I'm happy, okay? Because that essentially tells you how to use the formula. Nobody will read the paper, okay? But you can use a formula.
Can you say again where W comes from?
W is a choice. It's just a generic displacement vector. W is telling you how to, you see, you have 2 endpoints. The evaluation map gives you 2 endpoints. It's a pair of points in NE. You can take the difference, and the displacement vector fixes this difference. Does this make sense? Okay, so if you have several edges that you split, you will have a whole, you don't. Okay, how can I help?
I guess
No, make some sense. I mean,
I guess the question is, what is the meaning on the algebraic geometric side of this W vector?
Well, I'll explain in a second. That's exactly over here, right, Dan? So as Yixian already emphasized in her talk, a W displacement vector. What's a vector in the lattice where your fan of a toric variety lives? It defines a GM action. Okay. So similar here, you get a GM action first on the gluing stratum, and then an induced action on these on the kind of product M of X tau I. Or rather, actually, it's an induced action if you look at the evaluation map and you pull it back. Okay, so let's look at what the GM action does here explicitly. What are these curves? These curves have one vertex still, and the vertex maps to this leg. That means it has one component, but it maps to that toric divisor. And then it has these two legs. Oh, I missed one more point. So of course, here's another marked point. Let's see, we have still another marked point, probably here, okay? But these are the marked points we don't care. What I care is this marked point, which is a punctured point. Maybe I should use a different color. Okay, so this is the one, this is a splitting point. This is the one that you took care of. And the GM action that W specifies tells you that you kind of move everything into, well, the one on this part, you move over here. Yeah, so that's the induced action. And similarly, you get something over on the other side. And what you get is that your glued moduli space is rationally equivalent to the union of strata that are depicted by these two pictures. Okay. And while the union of strata maybe are hard to compute because it's not toric, yeah, it's the image of a toric map, but they are not toric strata, so they don't belong to Gromov-Witten invariance. Here it gives, you can easily compute this. Okay, so there are only two more slides, or maybe three. Let's go back to this broken line situation. Okay, so we had this picture, and I told you the edges we want to split are here. These are the edges in the wall, and then the incoming edge. And you split, you get tau in, the ones in the wall, and this tau 0, which is like the central one. The key insight here is that there exists a displacement vector such that we have only one split type. This delta of W appearing in Yixian's formula has only one type. And the picture, the cartoon I would draw here is as follows. Let's go, let's say we are in dimension 2 to draw pictures. So then we have a wall here. And before I split, there was just this stuff coming in and then all the stuff on the wall, okay, and then coming out. And now I split, which essentially tells you that I need displacement vectors at the endpoints. Let me put here endpoints that tell you how this gets moved. And then there would be types that, oh, this is an important thing, okay? The tau i's, this is what, tau s minus 1. The tau i's are confined to the wall, okay? This is just by dimension count. They cannot move left or right here. So if I have this displacement vector, it cannot happen that, that this wall, this tau moves out here, yeah? That just doesn't happen. So the only way you can fulfill this gluing condition is that you split this type of your central curve, this tau 0. And let's say, I mean, tau 0 can be easily split. That's just a vertex with a bunch of legs coming out, and you split it into S-1 vertices connected by a bunch of edges. And then distribute the edges depending on the lengths of the chosen lengths of your displacement vectors. Okay, so there is a choice where you order your displacement vector in the order that you want to order your taus, and you end up with this one single type. Does this make sense? So the whole formula over here that runs over delta of W will collapse and have just a single term. Okay, so that was lemma 1. And then lemma 2 is computing this index. And that's just some lattice index computation. I spare you the details. I mean, what you get is some factors that you expect. It has to come out right? Because we know what the rule is supposed to be. And what you get is one thing having to do with how this incoming vector is the relative position of the incoming vector to the wall. So if you take the projection from lambda sigma, that is sigma, right? This whole thing happens in sigma. So lambda sigma has a projection to the quotient by lambda p, the integral tangent vector of the wall, and that's a copy of z, and you take the length of the image of this incoming vector, okay? And then these other factors, kappa out, kappa in, kappa I, they have to do with lattice indices coming from the evaluation maps. Okay, so let's skip that. And then the result is that you can decompose the push forward under the evaluation map, some factor, there are no automorphisms, but there's some factor here. And then you have that, that is as before, right? No changes, the tau i's, oh, maybe I should say this. So what's the type now, right? So rho has an incoming thing that's just a tau in, unchanged, the same type. The types of the stuff living on the wall is also unchanged. And that's important because all hell breaks loose if you start kind of perturbing the tau i's. We have little control of what's happening. Well, here, we don't need to do anything, right? They just stay there. And then the only thing that is different is this rho 0, right? This is not a tau 0. It's not this kind of thing, but it is this kind of thing. Okay, so that's the only thing that changes. So the only difference between this and that, you see, is this kind of term. There's a rho 0 versus a tau 0. And of course, it's supposed to be a point. And so then let's unravel what this means. What's the left-hand side? That contributes to your count, to your broken line interaction with the wall P, something where I didn't tell you the details. And the right-hand side is the mx tau in is the broken line before the wall. Okay, so you sum over all these configurations, you sum over all incoming walls, or you fix an incoming wall, then this guy is fixed, and you look at what is contributing to the outgoing thing. And then the mx tau I is the stuff living on the wall, these 1-point invariants carried by this wall P. And then there's this one interesting thing, which is the m of x rho 0, which is the interaction term. Okay, I call it the interaction term. So we have to compute this interaction term. What is it? So fortunately, it's very easy. This is unchanged. I just copied it from the previous page, so you don't need to read it. But the lemma is just saying that the degree of this is 1. Okay, it's a simple computation. So either it's a point, then you do some computation on a moduli space of genus 0 curves with a bunch of points, or it's a P1, and then you do some kind of branch cover thing. And you can easily compute that this invariant is always 1. What is also interesting is that is also important for the scattering rule. If you pass through a codimension 1 cell of a polyhedral decomposition, you're supposed to pick up a curve class, namely the curve class C. And it comes out exactly right. Okay, so you see that this thing a priori is decorated by curve classes. Yeah, But the only curve class that contributes is actually D times C. And the rest, just bookkeeping, okay? So that's it.